Yeah, hi everyone. I'm very excited to be here today to talk about p4pktgen, our tool for automatically generating test cases for P4 programs. So this is joint work with Jehandad and Peter Athanas from Virginia Tech, as well as Andy Fingerhut from Cisco, and my advisor, Clark Barrett. As you all know, programmable network devices are becoming more and more common. And this is very convenient, but the issue is that whenever you introduce more flexibility, well, you introduce new places where bugs can sort of occur. So previously, you had to worry about your hardware, that the hardware is bug-free, but now you also have to worry about the P4 programs, or the programs that you're actually running, as well as the tool chains that you use to compile and run the programs on your hardware. And so one thing that you might be worried in particular about is that the program that you're actually running on the device corresponds to the program that you wrote. Now, one way to figure that out is to actually generate a lot of test cases and run them against your device and checking whether the test cases behave as expected. So in this context, in our work, we've been looking at P4. As you've heard today multiple times already, P4 is a programming language for the data plane of network devices that has been gaining a lot of traction. And so what our tool does is it automatically generates test cases for those P4 programs. Now, when you generate test cases, you ideally want to achieve some sort of coverage to make sure that you cover all the aspects of the program. And the way we do this is that we generate test cases for all paths in a P4 program. And we, in order to achieve that, we actually perform symbolic execution along concrete paths in the program. And for that, we had to do a formalization of P4. Now, before I talk more about p4pktgen itself, let me just give you a brief refresher of what symbolic execution actually is. So symbolic execution is an analysis technique that translates a program into a set of logical formulas to examine the behavior of the program on all possible inputs. And this allows you to reason about the program at the bit-level precision. Now, for the actual reasoning, symbolic execution engines usually use what's called satisfiability modulo theories, or SMT solvers. And what those tools do is they take as input a set of constraints, and then they either give a variable assignment such that the formula is true, or they tell you that the constraints are unsatisfiable, in which case you know that no such assignment exists. Now, so the task of p4pktgen is to actually take a P4 program and translate it into a set of constraints. And so here's at a high level how we actually generate test cases from a P4 program. Instead of parsing P4 ourselves, we actually use the p4c open source P4 compiler to parse the program for us, which makes our life easier and allows us to be independent from the P4 version. The P4C produces a JSON for us that we then actually parse and generate control flow graphs from. And then through those control flow graphs, we generate concrete paths that we send to our translator that then generates the constraints that correspond to that path. We then send those constraints to the SMT solver, and the solver will either tell us that the constraints are unsatisfiable, in which case we know that no packet exists for that path, or it will give us a variable assignment that we can use to actually generate test cases. We can then sanity check the test case that we generated by sending it to BMV2, which is an open source software switch for P4, to make sure that the path that our test case is actually taking corresponds to the path that we want. Now, to make things more concrete, let me show you how we translate a path through the parser of a P4 program. So P4 programs, they have they specify a parser that describes how the program interprets packets coming in from the network. And it does so by having a state machine with different parser states. So in our case, we have two parser states, parse Ethernet and parse IPv4, and we are given a path, a target path that we want to follow. So in this case, we want to go from parse Ethernet to parse IPv4 to parse TCP, and we want to generate the constraints for that path. Now, the way we do that is we basically follow this path and translate each of the statements along the path. So at first, we start with the extract statement in the parse Ethernet header. Now, the extract statement in a P4 program essentially consumes a bunch of bits from the input packet and assigns them to variables in your P4 program. Now, in our case, we actually model the input packet as a large integer of a fixed bit width. And so the extractions, we do them by extracting from that integer, generating expressions that extract from that integer the bits that correspond to the fields. And we store those expressions in our context. Now, the context is essentially just a map from variable names to symbolic expressions. Note that for just the extract statement, we actually don't get any constraints because, well, there hasn't been any decision made. The decisions get made when you get to a transition statement. Now, here we know that we would like to transition to parse IPv4, and we know that this transition is dependent on the ETH type variable. Now, the way we generate the constraint that corresponds to this statement is that we look up in our context what the symbolic expression for ETH type actually is, and we generate the constraint that this symbolic expression has to correspond to the value specified in the transition. And then we continue this process. We go to the next state, and we again model the extract statement, which updates our context, and we again add a constraint for the next transition. Now, in P4 programs, sort of the main processing of packets is happening in the match action pipeline, which is essentially a sequence of conditions and table applications. Now, for the conditions, they are very similar to conditions in C. And the way we translate those is that we actually translate the expression that corresponds to the condition, and then we either require that expression to be true or false, depending on the branch that we want to take. For tables, well, tables in a P4 program are executing actions based on a configuration set at runtime by the control plane. And so what we have to do is actually to generate those configurations in the form of table entries. And the way we do that is whenever a table is applied, we record the symbolic values of the keys at that point in time. We generate fresh variables for the action parameters. And at the end, when the solver gives us a variable assignment, then we work our way backwards, and we actually generate the commands for setting the table entries. Now that we've seen a little bit how p4pktgen works in translating paths into an SMT problem, let's briefly talk about some results that we found. So we tested p4pktgen on 4 P4 programs, ECMP, which is an example from our paper, 2 examples from the original P4 paper, and switch.p4, a large open source P4 program that we had to simplify a little bit to just only use the P4 features that we currently support. So in the case of the 3 smaller examples, we were actually able to generate test cases for all paths through the program in under 2 minutes, so that's fairly quick. In the case of switch.p4, that's not really possible because there are a lot of paths, but we were still able to generate thousands of test cases within the 30 minutes that we run for. Now, during the development of p4pktgen, we wrote a lot of small P4 programs, and we applied p4pktgen to them. And in certain cases, we realized that the test cases did not match what we expected. Now, in 4 of the cases, we realized that the bug was not in p4pktgen, but actually in P4C. And so we reported those bugs, and they were fixed. And for example, one of the bugs was that if you had a negation and then a conversion to a larger bit width, the sequence of those 2 statements were actually inverted. So the main takeaway from this, for us at least, is that bugs in P4 compilers are actually a problem, and that test cases can help reveal those problems. So in conclusion, we've seen that p4pktgen can actually be used to generate test cases for large P4 programs, and also that there are actually bugs in P4 compilers. Now, we are far from done. We've just begun with this project. We would like to extend p4pktgen to support all of P4. For example, we currently don't support checksums. We also are working on supporting branch coverage instead of path coverage, and we actually have a prototype implementation of that, which would help us, which would better scale to larger programs. And in the future, we would also like to add support for user assertions and actually test real P4 implementations. And with that, I would like to thank you for your attention, and I'm open for questions.